As far as I can remember, I gave you the definition of basic and basic feasible solutions, and maybe we can illustrate the situation with a little example. Here's an example in 2 dimensions as relates to the intersection of n linearly independent constraints. In this example, we've got a feasible region that looks like this. This is your polyhedral set defined by a bunch of linear inequalities. And let me just number these constraints. This one is number 1, number 2. Let me write them inside, actually. One, 2, 3 is, did I do this? I didn't do that, this one. Did I? Last time?
I think we did.
Let me just see your notes, because I don't really remember. No, this is something else. We did basic and basic feasible solutions, and after that, there's nothing. No, we used the same example for something else. Number 3, number 4, and number 5. So in this case, we have a bunch of points. For example, this one, let's just call it, for example, x bar. And then let's pick a point here, call it x tilde. And then let's pick this point, this outside point, call it x cap. Okay? So if you look at the system at x bar, for example, the first point, then the active set of constraints at this point are 2, 3, and 4. And for a basic feasible solution, for a basic solution, I need 2 linearly independent ones. Okay? I'm in 2-dimensional space here. So any 2 of them will do the job, actually, because you can see that their normals are linearly independent. Okay? So for this reason, if you pick, for example, row 2 times x equals b1, b2, sorry, and a3x equals b3, constraints number 2 and 3, if you happen to pick them as your linearly independent set, then you get a unique solution which is your x bar. And obviously that's in your polyhedral set. Okay? Why? Because number 3's line and number 2's line, they intersect at that unique point. So I don't care what the constraints are. They are whatever they are. Okay? All right, let's look at the situation at x tilde and x cap. Let's look at x cap first. Okay? So at x cap, my active set consists of which ones? 2 and 5. Right? Yeah, 2 and 5. So at this, if you look at the solution of the number 2 and number 5 constraints, this is the system you've got. And the solution will be, again, unique. And it will be x cap. It will be outside of the polyhedral set defined by the constraints. P is here. P is inside. Okay? Just in case, I erased it. So, all right. So, if you compare the 2 of them, this one with this one, in this case, you have a basic feasible solution. X bar is a basic feasible solution. This one is a basic solution, but not feasible. Now, what is the situation at x tilde? Well, in that case, your j of x tilde is, there's only one constraint, number 4, but you need two linearly independent constraints, or two linearly independent normals of these constraints. And so you don't have enough So if you're just looking at the fourth constraint, which in this case will be a single equation with two variables, which admits multiple solutions, no unique solution or multiple solutions. And so it's not basic. And of course, the picture also tells you it's not basic. It's not an extreme point, okay? Well, we haven't really matched extreme points with basic solutions yet. Nevertheless, I know that it's not a basic solution just because of the considerations we've got here. All right. Let me give you another example. Suppose my polyhedral set is defined now in 3 dimensions. The first one was in 2. There's one constraint which tells you that the sum of the variables is equal to 1. And then you've got the remaining constraints, x1, x2, x3 being greater or equal 0. Greater than or equal to 0. So this is your set. Let me just number these constraints. Let's call this constraint number 1, number 2, number 3, number 4. So the non-negativity constraints are number 2, 3, and 4. So in this case, if you picture this in the form of 3 axes, x1, x2, and x3. So you are in 3-dimensional space. You've got this equation which tells you that you should be on a plane whose intercepts are the unit vectors, right? Okay, so there's one here and one here. So the first unit vector is 1, 0, 0. This one is 0, 1, 0. This one is 0, 0, 1. Okay? Each of them is on the hyperplane. So you should be on this hyperplane, which has this triangular shape, but extending in all directions. Okay? So, in this case, your P is actually this triangular portion of the 3-dimensional space. Okay? Non-negativity as well. All right, let's look at this point. 0, 0, 0. And let me call it x bar. Yeah. Now, when you look at this point, what is j of x bar? Well, the constraints 2, 3, 4 are satisfied as equalities. So my active set is 2, 3, and 4. Okay? Do you have a linearly independent set? The first constraint, x1 greater than or equal to 0, the normal of that is the unit vector 1, 0, 0. Okay? Because x1 greater than or equal to 0 means the unit vector times the x, the first unit vector times x greater than or equal to 0. So, obviously, they are linearly independent. Any two. Since any two of them, pardon? Any three, sorry, you're right. We're in 3 dimensions. For a moment, I went back to the other one. Yeah. Any three are, well, there's only one set of 3. So the 3 of them are linearly independent. So then one is tempted to think that this is a basic solution because you've got 3 linearly independent active constraints. Their intersection is unique. It's this point. Okay? And so one is tempted to think that that's a basic solution. What do you think? Is it or is it not? If you look back to your definition, why don't you go and look back to your definition of basic solutions? Say it again.
Basic but not feasible.
Pardon?
It's basic but not feasible.
Okay, you think it's basic but not feasible. How many people agree with that? It's for sure not feasible. I mean, I agree with that part. Is it basic or not?
Basic.
Did you look into your definition?
Yeah, I keep in mind.
What does the definition say in part A and in part B? Do we have a part A and part B?
Yes.
Yes, yes.
In part A, x bar is a basic solution if j x bar includes I3.
Okay. And part B?
For A, there are n linearly independent constraints in j x bar. In part B, x bar is a basic feasible solution if it additionally satisfies all constraints not in j x bar.
Oh. Say part A again. Maybe we're missing something here.
X bar is a basic solution if j x bar includes I3 and there are n linearly independent constraints in
Okay.
j x bar.
Nothing is missing actually. If it includes I3, which is the set of linear equations, and there are n linearly independent constraints, including I sub 3, the index set of the constraints that are equalities. Does this include the index of the equalities? It doesn't. So, even though these are linearly independent, which is the second part of part A of the definition, this is not basic. Not a basic solution. Because it misses number 1. You're supposed to satisfy that. Okay? So, these are settled differences. I mean, you know, there's a reason why I'm giving you all these examples. Okay? All right. So, it's not basic. Fine. At least we know that much. And for sure, it's not feasible. Okay? Now let me do the following. Replace the first constraint, number 1, with, say, 1a and 1b. where 1a is x1 plus x2 plus x3 is less than or equal to 1. And the other one is the same thing, greater than or equal to 1. Okay? So obviously, any feasible solution to the pair will satisfy number 1 and vice versa. Okay? So P is now defined by 1a, 1b, 2, 3, and 4 constraints. Okay? It's the same P. Now, is the same point x bar a basic solution now? Of course, since I'm asking the questions, yes, it better be, because there's no, otherwise there's no point in going through this example. The answer is yes, because in this case, j of x bar still includes constraints 2, 3, and 4. But in this case, you have no equality constraints. So you don't have to do anything with equalities, strictly. And for that reason, since they are linearly independent, the three of them, yes, it is basic. Okay? So the same point is not basic in one case and basic in the other case, even though we're talking about the same polyhedral set. So the property of being a basic solution or not depends on representation. Depends on how you represent your polyhedral system under consideration. Okay? So that's the bottom line here. The property of being a basic solution depends on how you represent the polyhedral system or polyhedral set under consideration. All right. So that's enough for that. Let me just mention one more thing here. The case of having less than n constraints. So in this case, you have a polyhedral set, and P is defined by, say, some k constraints, but k is less than n. Constraints, half spaces or hyperplanes. Okay? In this case, there's no way you can have a basic feasible, or there's no way you can have a basic solution. Okay? And the reason is, to have a basic solution, you need n linearly independent constraints, but you don't have enough of them. No basic solution at all. So one example of this, if you are in two-dimensional space, but you have a single constraint which tells you, say, to be in this half space, yes, you have a polyhedral set, but there's no basic solution, no extreme point. You can see that. Okay? All right. Let me give you a theorem now. Let P be a non-empty polyhedron Polyhedron is the same as polyhedral set. A non-empty polyhedron in Rn and let X bar be a point of the polyhedral set under consideration. The following statements are equivalent. A, X bar is a vertex of P. B, X bar is an extreme point of P. And part C, X bar is a basic feasible solution. So, the properties of being a vertex, an extreme point, or a basic feasible solution, they're all the same, equivalent properties. Of course, to believe that, you need to prove these things. Now, either I leave the proof to you, so in the exam you prove it, or I go ahead and prove it, so you have a way of seeing or envisioning these things. Which one do you want? Hmm? The second one. Okay. But then I don't remember the proof. You know, maybe we should. I've no idea. Well, you know, we'll see if we can go ahead and work out a proof. All I remember is I had a proof that goes like this. A implies B, B implies C, C implies A. So let's begin with one part and see if we can work out a proof. Let's begin with A implies B. In this case, by assumption, you assume X bar is a vertex. You need to prove that it's an extreme point. Okay? To prove that it's an extreme point, you should be able to show that it cannot be represented as a strict convex combination of some two distinct points of P. All right. So we assume X bar is a vertex of P. So by assumption, there's a non-zero vector C such that something is true. What is that something? When you look at the dot product of C with X bar, it's strictly, was it greater than or less than? Which one did I give you? Greater. Oh, smaller than. Okay. That it should be less than, strictly less than, the dot product of the same vector with any other x for x in P except the point under consideration. Okay? That was the definition of being a vertex. So, let U and V, now I'm going with the extreme point business. Okay? Let U and V be points in P and let's take them here, okay, in P minus X bar. Let's take them both different from X bar. And lambda be a number in the open interval 0 to 1. So what I'm going to do is I'm going to take C transpose times lambda u plus 1 minus lambda v. Both points are different from x bar by my choice. So this is going to give me lambda c transpose u plus 1 minus lambda c transpose v. I know that since u is different from x bar, this should be greater than c transpose x bar because of being a vertex. Okay? This part is also the same. This is greater than c transpose x bar. And if I replace these dot products with c transpose x bar, of course, then I get a strict inequality here. Lambda times c transpose x bar plus 1 minus lambda c transpose x bar, which is nothing but cx bar. So what did I show? I just showed that this stuff at the very left is strictly greater than what you've got here, okay? Because of the inequality over here. Accordingly, lambda u plus 1 minus lambda v has to be different from x bar, because you've got strict inequality, okay? Is this enough? Yes, it is enough. You are not able to show, you are not able to express x bar as a strict convex combination of two distinct points of the set that are each different from x bar. Hence, x bar cannot be expressed as a strict convex combination of two distinct, well, did we say two distinct? Well, 2 points of P that are both different from x bar. Okay? And that's enough to show that it is not it's not an extreme point. Okay? There's a few other arguments you should add to this, but I'm not going to do it. You should be able to do that on your own. What are the additional arguments? Well, the way I gave you the definition, u and v had to be distinct, which means they are supposed to be different, and lambda had to be between 0 and 1. Here, we picked u and v to be different from x bar, so you should also look into the case when they are distinct, but one of them is possibly x bar, okay? And it won't work still because lambda is still not 0 and not 1. If you allowed it to be 0 or 1, it would have worked, okay? But that's too much, that's minor stuff that you should be able to work out on your own. So this part is okay. Now B and C. Of course, in an exam, you have to work out all the remaining parts as well. I'm just skipping that additional comments. So what do we need in part? The proof of B implying C. X bar is an extreme point. It implies that X bar is a basic feasible solution. Well, let me work out a proof using the negation of C implying the negation of B. If you prove this, this is the same equivalent to B implying C, okay? They are the same. So when you assume not C, that means, so assume X bar is not a basic solution, basic feasible solution. So if it's not a basic feasible solution, there are two possibilities. Either you have n linearly independent constraints which give you a unique solution, X bar, but X bar is not feasible. It's outside. Okay? So it's basic but not feasible. The other possibility is you don't have n linearly independent constraints. Now, the first case does not apply or is not a valid case. Why? Because X bar by assumption is inside P. Okay? So, for that reason, it's for sure feasible. So, the only remaining possibility is the other possibility. Since X bar is by assumption inside or in a point of P, then the active set J of X bar does not contain n linearly independent constraints. Remember that n linearly independent constraints means their normals are linearly independent. Okay, that's the way we define these things. Okay. Okay. Let's look at the span of these constraints or the normals that are in the active set. So you're looking at the rows of or the row vectors AI whose constraints are in the active set. Okay. So consider the span of this. Then, of course, this span, since you've got less than n here, even if they are linearly independent, you don't have n linearly independent. So the span does not span the entire space Rn. Okay? So, since J of X bar is less than n in cardinality, the span of these things is a proper subset of Rn. It doesn't include everything. Then there exists a vector D, a non-zero vector D in the remainder, in other words, Rn with span removed, okay, such that D is orthogonal to everything in the span. Of these vectors. Okay? It's orthogonal. In particular, D is orthogonal to each AI for I in the active set. Now, where do I go from here? Well, we're trying to prove that not B occurs, which means we should show that under the assumption of not C, we should be able to show that X bar is not an extreme point. We should be able to construct two different points whose strict convex combination gives X bar. Okay, that's where we should be heading at. I'm going to move from, or I'm going to use that particular D here. All right, how do we do it? For small enough epsilon, which is a positive number, consider the 2 points defined by x plus epsilon times, epsilon is just a positive number, this direction vector d, and x bar minus epsilon d. These are definitely different from each other because d is not 0 and epsilon is positive. So they are definitely apart. Okay? And my job is to prove that X bar is actually a convex combination of these if you take your lambda equals 1/2. Okay? But then first, for small enough X bar, we should show that these are in the polyhedral set. Okay? Otherwise, of course, things won't work. All right. So how do I show that these are in the polyhedral set? We have AI times X bar plus epsilon. So I'm taking the first point. I'm looking at this. And it's going to be AI times D. Okay? Now this part is 0. I know that for sure. And for the case AI is one of the I belongs to the active set, this part is equal to BI if I belongs to the active set. So this is an equality for every I in the active set. Okay? So all constraints in the active set are satisfied as equalities for the new point. For the remaining points, for the remaining constraints, so I'm giving an argument now for the case I is not in the active set. Okay? In that case, of course, what do we know? We know that this part is still 0. What do we know about this part? Okay, let me make one assumption to make life easy. Okay, let's go back to the beginning because I just realized that I don't want to complicate arguments too much. Let's make an assumption at the very beginning. Why don't you make a note here? Yeah, okay. So let's make the following assumption. Assume without loss of generality that P is defined by either greater than or equal to type constraints or equality constraints. So the less than or equal to type constraints, I'm ignoring them because if you have such constraints, you can multiply them by -1 and put them in this form. Okay, so there's no loss of generality here. All right, just to make the arguments a little bit easier. So using this assumption, I know that this part is strictly greater than BI, because the remaining constraints are inequalities, and they're all of the greater than or equal to type, and of course these are inactive, which means they are strictly greater than the right sides. Okay? All right, so this is true, which means that this entire thing is greater than BI for such constraints if you choose epsilon sufficiently small. Of course, if epsilon is actually, well, it doesn't really. Oh, wait a minute, this is not 0. Is it 0? No, this is not 0. Sorry. That's not 0 because now AI is not in the active set. The only thing we know is D is orthogonal to vectors in the active set. Okay? So this part can be anything, which means it could be 0, negative, or positive. But using sufficiently small epsilon, you can guarantee that whatever you've got here, if it's a negative number especially, if it's positive, of course, you have no problem. But if this is negative, you can make it small enough so the strict inequality is preserved. Okay? That's an important element here. I'm trying to reconstruct the proof from my head, so mind you, I may have to go back a little bit to revise the arguments. Okay? But this is the situation. So the conclusion here is, for small enough epsilon, the point x bar plus epsilon d is in P. It is feasible. It satisfies all of my constraints. Okay? Similarly, you can argue for x bar minus epsilon d in a similar fashion. Of course, you need to, essentially the same arguments, except that you've got minus here. Okay? Is also in the polyhedral set P. Since x bar is 1/2 x bar plus epsilon d plus 1/2 times x bar minus epsilon d, x bar is not an extreme point, because both x bar plus epsilon d and x bar minus epsilon d, they are two different points. They are both points of P, and you have a strict convex combination which gives you x bar. So we just proved not C implying not B. There's only one more thing left. Except that we're running out of time. So I proved A implying B, B implying C, and C, now we're working on C implying A. What is the XY is a basic feasible solution? And we should show that it's a vertex. Let's define a special C vector, which is the sum of the AIs for I in the active set. Okay? Then, when you look at C times X bar, C transpose times X bar, you're going to get, actually, yeah, let's make this transpose here. Because AI are row vectors, so C transpose. Okay, C transpose X bar is then AI X bar, I in JX bar. How much is AI X bar? Well, this part is BI, so this is simply sum of the BIs. I in the active set. Okay. And to prove that X bar is a vertex, I need to show that this number I get for CX bar is strictly less than C transpose X for any other X in the polyhedral set. So let's pick a point X in the polyhedral set and see what happens. Okay? I don't make it different from X bar yet, so it could be X bar. Nevertheless, let's just pick one. Then we have C transpose X, which is by definition AIX I in the active set for X bar. What do you think? Okay, good. Because of the star assumption, AIX, because it's in P, this is greater than or equal to BI in each term. Okay. How much is this? We just showed it. It's C transpose X bar. So what did I show? I showed that C transpose X is greater than or equal to C transpose X bar as long as X is in the polyhedral set. Equality in this inequality is possible only if, well, let's see. Only if X and X bar are the same. Why is that true? Well, if you permit equality here, you're going to get, let's see, how can we argue for that? If you permit equality here, you have n linearly independent constraints in J of X bar, so they admit a unique solution. So whenever you have equality, it should be the case that X is the same as X bar, okay? Since which system are we talking about? The system, this being equal to, since AIX equals BI for I in J of X bar admits a unique solution. Due to the fact that these AI in the active set being linearly independent. Well, there are n of them that are linearly independent due to the fact that there are n of them that are linearly independent. So let's just erase this. Okay? So if you have strict inequality, then so for x different from x bar, we have strict inequality, which means C transpose x is greater than C transpose x bar. Okay? And that's the definition of being a vertex. All right, let's take a 10-minute break here, unless you have questions, or you can bring your questions in the next slot. Okay?